Tonight, we're going to talk about the uniqueness of the Earth. And if you were looking at the newspaper or the internet earlier this week, you saw headlines in the paper or even Google, water found on Mars. Life is, there's the swimming pools are filled with Martians enjoying a nice balmy Martian summer. So, and you hear that, and so what I was thinking a few weeks ago was I wanted to go through and really address what makes a planet habitable. You always hear, oh, this is an Earth-like planet. Well, is it an Earth-like planet, or is it one they want to be an Earth-like planet? So I'm going to go through that. I've got some videos and some other things, so let's get started. As always, our mission statement for this organization, the Biblical Creation Science Group, is exalt Jesus Christ, teach the Bible, equip you, the saints, and then send you on your mission out there to tell the world, interact with people and tell the world. So I wanted to sort of try to tell you what I'm going to tell you. So tonight I'm going to try to tell you about how Earth is unique. God in infinite wisdom has made the Earth unique in so many different ways. And I'll go through a few of them tonight, but I can assure you there are more than I'm talking about tonight and more than probably anybody has ever listed. So we'll never know exactly how many wonderful miracles that are helping support and sustain our life on Earth. So one of the questions is, why are scientists seeking so desperately to find life on other planets? That we're spending billions and billions of dollars. NASA, most every dollar NASA is spending is trying to discover life on other planets. That's the only thing they're trying to do. And then I'll go through a list and see what are the real requirements for life on a planet, any planet. And then I'd like to finish up with really saying how unique the planet Earth is, how finely tuned. In the talk tonight, I'm going to show you factors which are required to have life, and I'm going to show you how finely tuned. They can't be too big, they can't be too little. They have to be right within a very narrow range in order to have life successfully exist on our planet. So these are just a few headlines. The upper left is the New York Times from the 28th of a few days ago. Early April, NASA ramps up hunt for extraterrestrial life on other planets. And then there was a whole series. If you were watching television, there was a series called Cosmos, which had a fictitious, computer graphic tour of the universe. And I took just a short sentence off of the website that they had. It says, weaving rigorous science with visual, emotional, and spiritual elements. And you can I guarantee you, I looked at some of those before I got so disgusted I just turned them off. There were 14 in that series. There was never mention of God. There was never mention of Jesus Christ. There was never mention of Allah. There was never mention of Zeus. So there was no mention of any deity of any pagan or conventional religion. And then SETI has been going on for years and years and years. That's a search for extraterrestrial intelligence. And that was one of the favorite brainchilds of some of the scientists that were 50 years ago. And they have found they're looking for signals in outer space from intelligent life with vast numbers of radio telescopes, and they found zero. Okay, so I wanted to try to make it kind of us versus them. So us, we believe in the Bible. So on the left side, the Bible is our Bible. And on the right, them, the New York Times or CNN or whatever you want to call it, is their Bible. That's what they live by. For us, we're blessed because we've got a book that tells us how to live, what to do, how to believe, where we came from, where we're going. It's great. They are looking for a substitute. either choose science, so-called, they worship science, or they worship aliens, or maybe they worship astronomy, or Nostradamus or something. There's always substitutes for God. Even right at the beginning, when the Garden of Eden, did God really say? So that's always the challenge to mankind. And we know and love our God, and they're frantically searching all over the universe for something to replace God, either here on earth or out in outer space. So just start with a few Bible verses. In the beginning, God created the heavens and earth. Pretty straightforward, the first words in the Bible. In John, in the beginning, all things were, in the beginning was the Word. All things were made through him, and without him nothing was made that was made. Pretty clear. Isaiah, it says, he formed the earth. It says, for thus saith the Lord, that created the heavens, God himself that formed the earth and made it. He hath established it. He created it not in vain. He formed it to be inhabited. So he's telling us that he made the earth to be inhabited. That's why it's so perfectly suited for our life here. And then Romans, for since creation of the world, invisible attributes are clearly seen, being understood by the things that are made. And finally, what are those lights in the sky? God said, let there be lights in the firmament of the heaven to divide the day from the night. Let them be for signs and for seasons and for days and for years, and to give light on the earth. We need light on the earth to be able to have warmth, to be able to eat, because we have photosynthesis with the plants. And he made a greater and lesser light. He also made the stars. So to give light on earth. And then in the end of that stanza, it said, God saw that it was good. So what he made was good, which means in our terms, perfect. So this is a famous photograph. How many have heard of Carl Sagan? He's a famous astronomer. He also had a television show years ago, before he passed away, called Cosmos. And he was an astronomer, but he became very famous and very popular. And what he was involved with was he worked on this Voyager. So they took a spacecraft, they sent it heading out of the solar system. So they wanted it to go outside the solar system. So it went for years, and what they did was they sent a signal to the spacecraft to turn around and take a picture of Earth. So this is a picture, that dot is Earth, and they call it the pale blue dot, or he called it the pale blue dot. He wrote a book about it. And that dot is Earth seen from Neptune, near Neptune. So that's the Earth seen from a very far distance. It's 40 astronomical units. An astronomical unit is the distance between the sun and Earth. That's 93 million, approximately 93 million miles. So that's one astronomical unit. So that's 40 times that distance. And there was a big, a lot of conjecture, and the feeling that they wanted to convey with this picture is, well, we're a dot. We're just a single little minuscule dot floating in space in a solar system that is so small in a unusual, or just a very ordinary galaxy, the Milky Way, and that's in some far corner of the universe. So we're nothing, we're nothing. We're not special. And so this is, I pulled this off, I put a little black box there. That's to censor some of the things that were being said. There were some actual comments that I thought were inappropriate, so I censored it. But this is a guy who is going to talk about how many stars there are.
I'm Fraser Cain, the publisher of Universe Today. And when we look at the night sky filled with stars, it's hard to resist counting. Just with the unaided eye in dark skies, you can see a few thousand stars. If you had perfect eyesight and traveled to completely dark skies in both the northern and southern hemispheres, and there was no moon, you might be able to count to up to almost 9,000 stars. With a good pair of binoculars, that number jumps to about 200,000. And with a small telescope, you should be able to count up to 15 million stars. So how many stars are there in the Milky Way? According to astronomers, our Milky Way is an average-sized barred spiral galaxy measuring 120,000 light years across. Our Sun is located about 27,000 light years from the galactic core in the Orion arm. Astronomers estimate that the Milky Way contains up to 400 billion stars of various sizes and brightness. A few are supergiants, like Betelgeuse or Rigel. Many more are average-sized stars, like our Sun. The vast majority of stars in the Milky Way are red dwarf stars, dim, low mass, with a fraction of the brightness of our Sun. As we peer through our telescopes, we can see fuzzy patches in the sky, which astronomers now know are galaxies. These massive structures can contain more or less stars than our own Milky Way. There are spiral galaxies out there with more than 1 trillion stars, and giant elliptical galaxies with 100 trillion stars. And there are tiny dwarf galaxies with a fraction of the number of stars. So how many galaxies are there? According to astronomers, there are probably more than 170 billion galaxies in the observable universe, stretching out in a region of space 13.8 billion light years across in all directions. And so, if you multiply the number of stars in one galaxy by the number of galaxies in the universe, you get approximately 10 to the power of 24 stars. That's a 1 followed by 24 zeros. That's a septillion stars. But there's more than that. The observable universe is a bubble of space in the 13.8 billion light years in all directions. It defines the amount of the universe that we can see because that's how long light has taken to reach us since the Big Bang. Astronomers have estimated the actual universe is at least 93 billion light years across, with only a fraction of that will ever be observable to us. So add another couple of zeros to that total number. That is a lot of stars in the universe. Thanks for watching.
So around the stars, astronomers have discovered that there are planets other than the sun. So other stars out there have planets, and so they call them exoplanets, meaning outside the solar system. And the way they can tell that there are planets is when you're looking at a star and one of the planets goes in front of the star, the light you gather from the star goes down ever so slightly depending on the ratio of the light, the size of the star versus the size of the Earth. So the sun, our sun, is 1,000 times larger than our Earth. So if alien was looking at the sun, our sun, and the Earth, our Earth went in front of it, then the level of light coming from our sun would go down by 1/1000th of an amount of light, and then when our sun passed over it, it would go back up. So that's how they tell, and that's where all of the conjecture is. They're looking at things traversing in front of these stars, slightly dimming the light that they're getting, and say, oh, there's an exoplanet, and there's another one, and there's another one. So they like to use this phrase, Earth-like planet. You see that in the newspapers, you see that in books and television and a lot of places, Earth-like planet. So one of the things I'm going to do tonight and try to show you how many factors they're going to have to match to have an Earth-like planet. And this is just as they've launched a space probe that's a telescope like the Hubble telescope. They call it the Kepler telescope. And that's out looking 24 hours a day, 7 days a week for these exoplanets. And they've found hundreds and hundreds of exoplanets. As time goes on, they discover more and more. So that's not a surprise that there are other celestial bodies circling around other stars. But the thing is, how Earth-like are they? And so I just put this view graph together for our little neighborhood, the rocky planets, or the terrestrial, what they're called the terrestrial planets. Those are Mercury, Venus, Earth, and Mars. You look at the distance from the sun. So the Earth is 1 astronomical unit, 93 million miles. So Mars is 1.5 times that, and Venus is about 3/4 that distance from the sun, and Mercury is only 38% of that distance. But if you look at what atmosphere is on these planets, these are the ones we know and we've sent space probes to. We've landed on some of them with space probes and have identified what a lot of the properties of each of the planets are. You see that Mercury has virtually no atmosphere at all. It has they call it trace. It can't hardly be measured. It has sodium and hydrogen and helium and potassium in the. It's a weird atmosphere. There's no possibility. And oh, by the way, the surface temperature is 800 degrees Fahrenheit. So that kind of, you got to wear SPF 12 million not to get a kind of sunburn there. Then you go to Venus, and that's the one that everybody's freaking out. Oh, we're doing, with the global warming, we're going to have a runaway greenhouse effect like Venus. Well, we have 0.04, if you came to the last lecture on global warming, we have 0.04% carbon dioxide. They have 96.5% carbon dioxide. There's only slightly over 3.5% of the atmosphere that isn't carbon dioxide. So there's a tiny, tiny little difference between the two. And then our pressure, and the pressure on Venus, because of the atmosphere, is actually 92 bars. So 92 times the pressure of the material that's in the atmosphere. If we have 14.7 psi, they have 92 times that. So it's a crushing pressure. Earth, of course, has a very mild temperature, averaging 60 degrees. If you average from the tropics to the poles, it's about 60 degrees. And Mars, it's minus 81 degrees. Does have water. I mean, we've known there's been ice cap or ice on the poles of Mars for 50 years. So that wasn't a surprise. They say, oh, there is liquid water. Well, we'll see. So I just wanted to show you that. So none of these planets are, even though Venus is about the same size, it has the same sun as we do, and Mars, the likelihood of finding any kind of life that would be bigger than a microbe would be virtually impossible. So let me play this video. This is from a movie called Privileged Planet.
Since 1995, this search has extended beyond our solar system, as astrobiologists have identified more than 100 planets orbiting nearby stars. Each of them is a gas giant, much like Jupiter. While few scientists believe that these alien worlds can sustain even simple life, their discoveries represent important steps toward answering a question that will shape astronomy in the 21st century. Are habitable planets rare or common in the universe?
I'm an astrobiologist, and the area that I've done the most work in lately is the field of extrasolar planets. What motivates me is just to examine the conditions necessary for life and look elsewhere in the universe and see if those conditions are met anywhere else. And the answer could be yes, and the answer could be no, and either answer is interesting.
Guillermo Gonzalez works as a research scientist in NASA's astrobiology program. His interest in this field is tied to his early fascination with the prospect of life beyond the Earth.
I grew up in the 1960s, and like most other people of my generation, I was really amazed by the Apollo lunar landings, and that really inspired me and had something to do with my getting interested in astronomy. In my early years, I came to believe very strongly that there must be other civilizations out there and that the galaxy was teeming with life. And so I was a strong supporter of the search for extraterrestrial intelligence. My belief wasn't based on any real hardcore scientific arguments. It was just the impression that I had that the galaxy was such a big place. And I didn't give the other side of the equation much thought. In other words, there's two sides of the equation. There's the number of stars, the number of trials, if you will. But the other side is the factors. It takes a lot of factors to have a habitable planet. in a planetary system.
So this is the equation I came up with. This is the only equation I have the whole night. We're going to study it, and this is going to tell us whether we have life or we don't have life. And so let me explain it to you. So the equation with the n is, so n is the number of planets with life in the universe. So that's what we're trying to find out. Then the next factor, so we know we have Earth, right? Everybody's alive here, we have Earth. We agree the number has to be 1, at least 1, can't be lower than 1. So then you add to 1, there's two things. So we have S, which is the number of stars in the universe. And we heard from the fellow who was telling us how many septillion stars there were. He said there was 10 to the 24th, and then to add a couple more zeros, because we can't see some of the stars because the light hasn't gotten to us yet. So that's 10 to the 26th. That's a big number. And then just for argument, I set the average number of planets around each star as 10. So we have 8. Pluto got kicked out. That would have been 9, but we kicked out Pluto because it's misbehaving as a planet. So we call 8, but you could call it 9. You know, there might be some that have 15 and some have 5, but they probably don't have 10,000 planets circling a star, and they probably don't, you know, there may be some with 0. So I just took 10 as an average, and that number is just for convenience. So if you multiply S times T, that's the number of stars in the universe, times the average number of planets per star. So you multiply those two numbers together, so the total number of planets that could possibly have life in the universe is 10 to the 27th. 10 with 27 zeros after it, or 1 with 27 zeros after it. Now the factors, you know, you heard Guillermo Gonzalez talking about factors. So those factors I've called P. So there's a probability. So P is the probability of a critical factor of life. So the probability in anything, rolling a dice or flipping a coin, the probability is a fraction between 0 and 1. So with a coin, you flip it, it's heads or tails. So 50% or 0.5 probability of head, 0.5 probability of tail. If you have a dice, a regular dice, 6-sided dice, you roll the dice, there's 1 chance in 6 it will be 1, 1 chance in 6 it will be 2, etc. So the probability of getting any specific number is 1 divided by 6 for a die. So what I've done is I found a paper where somebody who wasn't a creation scientist, they went through this long list. There's 68 critical factors that I'm going to talk about tonight, show tonight, and took each one of those 68 critical factors and made a probability. So the probability of having water, you've got to have water for life, that's some number between 0 and 1. What's the probability of having a temperature that where life can live? It's not 800 degrees and it's not minus 200, so that has a probability, and so on. So each one of those numbers, P1, P2, P3, you take all those numbers, and since they're independent, you just multiply them all together, and that gives you the total probability of all of those things being satisfied simultaneously. And so that number times the number of planets gives you the number that we have to add to 1 and tell us, is it 2, is it 20,000, is it 100,000? So is that clear? I can stop if there's any question, because this is critical. Okay? So we're looking at the factors. So I'm going to go through these 68, and I'm not going to do all 68. That's way too many. I don't have enough days in the week to do that. I'm just going to look at 22. So, but I'll show you the other ones. So that's the probability. So let's start with the first one, which everybody talks about, and this is the distance between the parent star and the planet, and that's called the habitable zone. And so the way, oops, back. So the way this works is up at the top, I gave it a number. So this is the first factor we're looking at, the distance from the parent star to the planet. the 1310 or whatever those blue numbers are, those refer back to another paper I can give you if you are interested, so you can tell that I'm not cheating. This is from a published paper by a bunch of scientists. And then the factor, the P1, is what their estimate was. What is the probability? They said the probability of having a planet in the habitable zone is 1 in 1,000. So that would be 0.001. So that's their estimate. One planet out of every 1,000 that are out there would be at the right distance from their star. Okay, so that's, and then down below I've got a bunch of the other 68 that I'm not going to really talk about. So this one I'm going to talk about. So this is a little diagram to show you what the habitable zone is. And really it's talking about what the surface temperature on the planet is. If it's 800 degrees Fahrenheit, there's no life. If it's minus 200 degrees, there's no life. So this is the zone. The green area is, you see the little planet circling around a star. And if it's in that zone where it's not too hot, it's not too cold, they called it the Goldilocks zone, then you call that the circumstellar habitable zone, CZ or C8Z. And that means that you can have life there, and you probably can have liquid water. So let me go. This is a diagram, and this is for our solar system. So you see in the middle, you see the yellow dot is our sun, and you see the Earth. The Earth is at 1 AU, 93 million miles away. And so that blue band is, we are right in the middle, exactly in the middle of the habitable zone. So for our planet, and we see that the closer planet to the sun, that would be Venus, they're not in the habitable zone. And the further out planet next to us is Mars, they're not in the habitable zone. So if you think like you do a computer experiment, you say, okay, well, what if the sun, or what if the star had, and this is calculated on mass. So what if the star was only 3/4 as massive as our sun? So if you look at that and you come across, you can say that for a star that has a mass of 3/4, this is a half, this is 1, so this is in the middle. So a 3/4 mass star would have a habitable zone that Venus would be in the middle of. And the other one is if you took a star that was 1.5 times more massive than our sun, then Mars would be in the habitable zone and the Earth wouldn't. So it's critical to know what the mass of the star is, and that determines uniquely what the habitable zone is. So let me run this little movie.
In liquid form, water is an extraordinary substance, and its existence hinges upon another factor essential to complex life: a planet's distance from its home star.
It's like what they say in real estate: location, location, location. A habitable planet lives in what we call the Goldilocks zone. It's not too hot, it's not too cold, it's just right. And when I say just right, I mean just right for water.
Liquid water really helps define the habitable zone. If it's too hot, again, the water just boils away, you just can't get condensed water. It's too cold, as in Mars today, it freezes out.
Within our solar system, the habitable zone is relatively narrow, beginning well outside the orbit of Venus and ending short of the orbit of Mars. If the Earth were just 5% closer to the Sun, it would be subject to the same fate as Venus: a runaway greenhouse effect with temperatures rising to nearly 900 degrees Fahrenheit. Conversely, if the Earth were 20% farther from its home star, carbon dioxide clouds would form in its upper atmosphere, initiating the cycle of ice and cold that has sterilized Mars.
The presence of liquid water is a necessary condition for life, but it's not a sufficient condition. After all, there may be liquid water under the frozen surfaces of Mars and Jupiter's moon Europa, but there's very little chance that complex life exists in either of these places. You see, contrary to what the Copernican principle might suggest, the recipe for life is much more complex than just add water.
So that the habitable zone sets the temperature. But that doesn't say you have water. So having water and having the habitable zone are independent. So the astronomers who looked at these factors, they said, well, what are the chances of having water on your planet? And so this is P2, that's the second factor. And they said that is also 0.001. So 1 chance in 1,000 that one of these planets that are out there has water. And we know that our cells are 70 to 95% water. The abundance of water, the Earth is covered with 71% of the surface is covered with water. So we have an abundance of water. And they talk about water on Mars. They find a few canals or little rivulets of water that seem to have gone from one place to another. And everybody's standing and cheering on the tops of buildings. We have 71% water. How grateful are we that we have water on our planet? So that was factor number 2. I think I'll skip over that one. The parent star luminosity. So this is factor number 3, and there's a whole bunch of more ones. So these are part of the 68, the ones with the dots, but I'm not focusing on those. So this is the luminosity of how bright is the light that you get from the stars. And they figure the correct amount of light from our star is 0.0001. So 1 chance in 10,000 that you have the right amount of light. And let me show you with a couple of graphs why this is important. So this is a plot of the luminosity on the left. This is a logarithmic scale. So this is 1, 100, 10,000, a million. Factors of 100. And then here is what they call the surface temperature. So that defines what the spectrum of light that comes from a planet is. And you see this blue line where our sun is. The sun is, I've colored red. So that's on what they call the main sequence. So most of the stars are on a line that can be connected that goes from very high brightness to very low brightness. And so those are called main sequence stars. The sun is part of that main sequence. Below that are very dim stars, but they're white, and that's called white dwarfs. These over here are colored yellow or red because they're called red dwarfs because their light is mostly red. And then you have these giant stars up here that are called the red giants, and they put out 10,000 times more light, 10,000 times more light than our sun. So you can't even imagine how much that is. And there's some equations that we have that relate the mass of the star with the luminosity, and that's well known. There's a lot of things that are very well known. But the key thing here, and we touched on it a little bit when I talked last week about the sun's participating in the Earth's climate, is we have to look at the luminosity. So that's here in this column, and the mass. These two are related. There's a relationship. And so what they say, if the luminosity of a star is 1, then it has the same luminosity as our sun. And if the mass is 1, then it's always compared to the mass of our sun. So we normalize everything. So you're saying, how much is it compared to our solar system? And then it tells you what the effective temperature is. If you know what the effective temperature is, you know the radius of the sun or star. And if you know that, then you know what the wavelength is that comes from the star. So this is a lot of background, but let me show you graphically what that means. So if you look at what the sun produces, the sun, which is, I put here, mass equals 1, luminosity equals 1, that produces a spectrum of light, which is absolutely right in the middle of the visible region. So the sunlight, when you see it hitting on a white piece of paper, is white. It has all of the colors of the spectrum, and that just happens to be perfect for photosynthesis. So for growing plants, they prefer to be in this sunlight from our sun. If you happen, so I did a comparison, if you had a star which had a mass that was 3 times what the mass of our sun is, then its spectrum would be shifted to ultraviolet. That ultraviolet light is deadly. It would be causing skin cancers. It would be causing sunburns. We would, again, have to have SPF 1,000,000 just to go out and experience the rays. We'd have to live in things that prevented the sun from ever touching our bodies. And conversely, again, I'm saying there's all of these things. You can't be too big, you can't be too little. If the sun were half the size, then its spectrum would be shifted to the infrared, and the plants wouldn't be able to use it. It would be invisible. We wouldn't see the light because our eyes are not attuned. How is it that our eyes are tuned to see light, and our sun just happens to be putting out the light that our eyes can see? Is that a coincidence, or is that an act of God? So those are the kind of things that you have to look at, and I'll give you just a little video here.
If we find life out there, especially complex or even intelligent life, it will be around a star similar to our own.
We orbit what is known as a spectral type G2 dwarf main sequence star. It is well suited for our needs. If the Sun were less massive, like 90% of the stars in the galaxy, the habitable zone would be smaller. To remain within its boundaries, the Earth would have to be positioned closer to its star. Here, increased gravity would lock our planet's rotation into synchronization with its orbit. While one side of the Earth continually faced the Sun and increased radiation from solar flares, the dark side of the planet would lay shrouded in perpetual cold and ice. It is unlikely complex life could tolerate these drastic extremes in temperature.
A lot of things went right on Earth to have yielded complex life, absolutely.
The number of factors that have been postulated has grown. Currently, the typical number you would see is, in a typical list, would have something like 20.
Now it's 68. So this, as I said, this is an old movie. But if you look at Mercury, Mercury is so close to the sun that it has experienced exactly what they talked about, this locking. Mercury doesn't rotate. It's like the moon. The Mercury is always one side is facing the sun as it goes around, or facing the sun as it makes its orbit. Like our moon, we see the same side of the moon because we've locked the moon with our gravity, so it's not spinning. So we don't see, that's why they call it the dark side of the moon. We don't see the other side of the moon. So that's what would happen to us if the mass of the sun were much less. Okay, so here's magnetic field, the fourth factor, more factors down below. That has a 1 chance in 100, so it has a probability of 0.01. And what it is that our Earth has a liquid core of metal. And that metal, because the Earth is spinning, is in constant motion. So if you have currents flowing in a circular pattern, then you get effectively it's electromagnet. But we know the Earth is magnetic. We can measure it with a magnetometer. And what happens is the solar wind, again, we talked about the solar wind influencing the weather on Earth, but we have these charged particles. The solar wind is not a wind of air, it's a wind of charged particles, of protons, of electrons, and of helium nuclei that are bombarding the Earth. But because we have this wonderful magnetic field, we have a force field. We shield ourselves. All of those particles that are bullets coming right at us, they actually go around the outside of the Earth because the magnetic field takes them around and guides them so they harmlessly pass by us, like Passover. So that's critical to maintaining the habitability of Earth. So how do they know if somebody starts spouting off to you about planets and being in the habitable zone and we think there's water there, say, does that planet have a magnetic field? How do you know? I'm going to skip that one. And if the magnetic field can't be too high, there are things that they call solar storms. When the sun emits a burst of energy, if the magnetic field is too strong in certain areas, we see the aurora borealis. That's the interaction of the charged particles with the magnetic field of Earth, but we can actually have potential electrical effects that affect our grid system. So the distribution of electricity throughout the United States, throughout the world, Canada, there was a big solar storm that hit, and because Canada is at the closer to the North Pole, it hit Canada much harder, and that tore up their grid system, and it cost the Canadians over $6 billion to repair all of the blown transmission lines, all of the transformers that blew up and everything. So having too much magnetism in the Earth is also very damaging to the infrastructure that we've built as intelligent beings. The albedo, we talked about this a little bit last week, and here are more factors. So this is factor 5 of the 22 I'm going to talk about. But the albedo is how much of the sunlight that comes to Earth is reflected back. And so in the red box, as we discussed last week, the cumulative or average albedo for the whole Earth, taking in clouds and forests and oceans and roofs of houses and everything, is about 31%. If that went up to 50%, then a lot of sunlight that does strike the Earth wouldn't, and we would be a much, much colder place. And if it was much lower, we would receive more energy and we'd be a much hotter place. So God made that just right in order to sustain life. And he built the ocean so that if we start getting too hot and it interacts with these cosmic rays to form clouds, then it cools it off. So we have a built-in mechanism for thermostat. So if it gets too hot, the clouds cool it down. If it gets too cold, the lack of clouds heat it up. And that's the way God has of controlling the temperature of the Earth. And then we've got two other factors. These are 6 and 7. This is oxygen in the atmosphere. There's no oxygen in the atmosphere of the other Mercury, Venus, and Mars. Nitrogen, we have a lot of nitrogen. So we have about 21% oxygen. The rest is pretty much nitrogen, and then there's a few trace gases like water vapor and carbon dioxide, a small 0.04% carbon dioxide, and I'll talk about that in a minute. And so we hear about these cycles when we talked several times in this lecture about God has made everything in a cycle. We have a water cycle, so the evaporation from the ocean goes up into the sky. The wind blows the clouds over to where the land and the mountains are. The rain comes down, it turns to snow, or it just is rain, it runs off and it fills the ocean, and then this cycle happens over and over and we get clean water. It's God's way of giving us clean water. Is that happening on all these exoplanets? No. And we have a balance between air being breathed by animals. The animals take in the air, they give out CO2, so we're breathing out CO2, taking in oxygen, breathing out CO2. The CO2 goes over to the plants love it, that's what plants respirate on is CO2. They breathe in the CO2 and they turn that into oxygen. So again, it's a cycle. We're changing oxygen for CO2, but the plants need the CO2, the animals need the oxygen. And the same thing for nitrogen. So nitrogen, is, as I say, is about high 70s, almost 80% of our atmosphere. The nitrogen is critical for the plants also. So the nitrogen in the air gets converted to nitrous oxide, NO3 or NO2, or ammonia, NH4, either through bacteria or through lightning or other effects that are happening, and that's the fertilizer along with animal waste. That's the fertilizer that makes the plants or allows the plants to grow. So if we didn't have the nitrogen in the air, there wouldn't be the plants. If the plants didn't grow, then we'd have nothing to eat, and the animals couldn't eat anything, so all life would die if we didn't have nitrogen to make the plants grow. So it's critical. So everything, again, is a cycle and is in balance. I think I'll skip that one too. So this is one thing, maybe Gary knows this through his military days. So I was wondering, so I looked up, what's the correct level of oxygen for animals to breathe? And the optimum range is between 19.5 and 23.5%. And we're a little over 21%. Isn't that a coincidence? So what happens if you get below, say, 17%? And it says you start losing your mental abilities. You know, that's why you have to wear the oxygen masks in planes or going up in the Himalayan mountains. If it's below 10%, then you become nauseous and you can start losing consciousness. And below 6%, humans die. So we're in a range that is exactly in the sweet spot between too low and too high. How about too high? Well, we can breathe pure oxygen for short periods of time. They give it to you in the hospital and things like that. But if you lived for an extended period in 100% oxygen, it would start attacking your tissue and cause your muscles to stop functioning. You'd start twitching. And if you lived in 100% oxygen for a long period of time, you'd die. So again, God has the plan, He has the number, He has set all of the processes in place to control it to be what it has to be. I'm wondering what the ratios are in that exoplanet they're discovering today or tomorrow. Carbon dioxide and water vapor, again, that was touched on a little bit last week on the global warming. And what we covered in that aspect was that those two gases are called greenhouse gases. So those gases are transparent to the sunlight that's coming in. So the light that we can see passes through CO2 and passes through water vapor and heats the earth. That's where we get our warmth from. We don't get it from volcanoes or underground sources of heat. You don't touch the ground and feel a hot foot. But those gases trap the radiation that then is leaving the earth, and it acts just like a greenhouse. It has a glass window over it, and it contains the heat within that thin shell of the environment that's right over the earth. And last week we discovered that if we didn't have those greenhouse gases, those trace amounts of CO2 and of water vapor, just the right amount, our planet would be 33 degrees Celsius colder than it is. So instead of being at maybe 15 to 18 degrees Celsius, the whole Earth, the average temperature across the whole Earth would be minus 15 degrees. And so, you know, there would probably only be a small band of land right around the equator that humans and other animals could even live, because the rest of it would be frozen over. So the greenhouse gases are imperative, and having the right amount, not too much, not too little, that's what you need. Ozone. We had a crisis years ago where we were having CF4 gas released into the air, and people determined that was threatening the ozone layer. You remember that? And they took pictures of the ozone shrinking over the poles and things like that. Well, the ozone, you know, that was a good thing. We actually stopped the depletion of the ozone. The ozone is there, and what the ozone does is, this little diagram is, there's, depending on what the wavelength of the ultraviolet light is that's coming from the sun, outer space, they have broken it up into 3 bands. So the band that has the very shortest wavelengths and the most damaging, they call that UVC. So that's a cancer-causing kind of UV rays. And that is blocked 100% in the ozone layer. So the ozone layer just removes all of that. UVB, which is a slightly different frequency, still not, you can't see it with your eyes, that is removed 95% of the UVB, and that's the ones that really do the damage to your skin. And that's only 5%. So some of the sun lotion that you put on, but most of the material we get is UVA, which is a frequency closer to visible light, and that's only 5%. So that's what you use as suntan lotion, so your skin doesn't get dried up and wrinkly. So even the ozone is built into the atmosphere to control the UV. So God made the sun. It has a lot of light and a lot of particles that it generates in order to have this controlled nuclear bomb that's going off in our sky every minute of every day. Sometimes we can see it, but at night we can't because it's on the other side. But that bomb is going off, and to protect us from it, he's given us ozone and given us CO2. And we have all of the magnetic field. All of these things are necessary to preserve the planet that's living next to a thermonuclear bomb. So you have to have every planet that they claim has the potential of having life. It has to have all of those characteristics. Without any of them, there's no life. So I hope I'm gathering your attention, okay? So this is number 12, moving right along. Gravitational interaction with the moon. And so you can't be too close, you can't be too far. The moon actually stabilizes the Earth like a spinning top. If you've ever spun a top, it has a mass that spins around, and you can spin it and it'll spin for a minute or two and before it falls over. If you try to do that with a pencil, the pencils don't spin a half a turn and then fall over. So the moon, because it's linked to the Earth, it's like a counterweight. Maybe it's like your engine. It's kind of swinging around there, and it's self-stabilizing the Earth. So it allows us, our Earth is tilted at 23 degrees, and so we have the ability to have very moderate summers, very moderate winters by having that stabilized. And they've done computer simulations that they said if the moon wasn't there, this large, relatively large moon, compared to the size of the Earth, that the Earth would flip-flop around 85 degrees. So I think I will play this video.
For a size of planet like Earth, our moon is big. The current thinking is that if our moon didn't exist, neither would we.
1/4 the size of the Earth, the moon's powerful gravitational pull stabilizes the angle of its axis at a nearly constant 23.5 degrees. This ensures relatively temperate seasonal changes, and the only climate in the solar system mild enough to sustain complex living organisms.
Okay, so then another factor is having a large planet in your solar system. So we have Jupiter, and actually they've done, computer simulation, and it doesn't happen with just Jupiter. You actually have to have a bunch of large planets. So we've got Jupiter, we've got Saturn, we've got Uranus and Neptune. So we've got 4 planets out there. And what are the planets doing for us? Well, they're comet eaters. Those planets, when we have anything that comes into the solar system that potentially could be threatening to our planet, those planets have such high gravitational pull, and there's so many of them, not just one, but there's 4 out there roaming around, sucking up any potential dangers. And this was 2009. They have a telescope that was trained on Jupiter, and you see that dark spot, which was a comet collision. And then we remember in 1994, the Shoemaker-Levy, they made a big production out of that. The Shoemaker-Levy comet was coming in, and then it broke up into a whole bunch of it was like a set of beads that came in, and it was like a machine gun that just plowed into Jupiter. So Jupiter is like our protector. Jupiter's out there sucking up these these flying objects that could come into the solar system and smash our planet. So there's another unique feature. Does the planetary system that these exoplanets live in, do they have Jupiters out there protecting them, or are they just at the mercy of what comes in might hit them? The atmospheric pressure and the atmospheric transparency are critical. So this is 14 and 15. Here's a couple more factors down here that I didn't, but their probability, this is a 10th and this is 100th for the transparency and for the pressure. And what we have is the water cycle. You think about it, the air has weight, right? You run your hand like this through the air, you can feel it. If there had no weight, you wouldn't feel anything on the hairs on your arm. And so what happens is the oceans are heated up, the water evaporates, and then the wind blows. The onshore breeze, we call it fog. So when that happens to the ocean, that carries the water vapor up into the mountains, where as it goes up the elevation, it loses the ability to hold water and it falls as snow. We remember snow, right? We were in California. We have a hard time remembering when it rained or snowed, but the snowpack, and then that melts and that gives us our fresh water, our dams and our fresh water that we drink. So the water cycle, the nitrogen cycle, the oxygen cycle, the carbon dioxide cycle, cycle. And that's just because God made everything is self-sustaining. His presence, His design is perfect. And then the other thing about a clear atmosphere, we have an atmosphere, you can go outside and look up and you see the stars. If our atmosphere was like Venus, or if our atmosphere was like Jupiter or Neptune, have clouds 24 hours a day, 7 days a week, we wouldn't be able to see anything. The light from the sun wouldn't be able to penetrate down to ground level. So none of the plants would receive enough light to have photosynthesis and make oxygen and make food for us to grow, because we pick them and eat them. Okay, and then eccentricity. So eccentricity isn't what I am, being slightly an oddball. Eccentricity means how much is it distorted from being a perfect circle. So when you look at I have a little cartoon down here if it plays. So if you look at the Earth and you measure how close the orbit of the Earth is to a circle, it's within 2% of being a perfect circle. And so that says that as we go around the sun, we're receiving the same amount of solar energy all year long, because we're tilted on our axis. Then the summer goes from northern hemisphere to southern hemisphere, so the Aussies get the sun when we're having our winter, and we get the winter when they're having their summer. So the tilt of the axis causes the differences in the seasons. But if we were like Pluto, has a 25% squashed, so it's like an ellipse, one of these things that are distended. When Pluto goes out there, if the Earth had a orbit that looked like that during the months when we were far away from the sun, we would be in big trouble. Then we would swing by and it would be normal, and then we'd go on the other side of the sun and we'd all be roasting to death. We'd have our air conditioners sent to 10 degrees trying to blow cold air. It would be intolerable. You couldn't have life if the orbit was not almost perfectly circular. And Halley's Comet, if you want to think about it, its trajectory is 97% uncircular. So it's way out there, and then it comes speeding in, and then it goes back out there again, and close and far. So we're blessed by having a circular orbit. Does this exoplanet that people are talking about, does it have a circular orbit? How do they know? Okay, and then the galaxy location. Where are we in the galaxy, in the Milky Way? Are we in the right spot? And this guy, Guillermo, and his team of people, they actually came up with this idea that in the Milky Way, there are places you don't want to be. So that green band that you see there, that's what they call the galactic habitable zone. So if you're not in that, you're too close to the center, you're too close to the edge, you're in big trouble, and I'll let him explain it. And so this is where we are with our sun, but let me play the video. This is kind of a cool one.
In 1997, Guillermo Gonzalez began a study of the Earth's specific location within the Milky Way galaxy. It would eventually lead him to more evidence of a correlation between life and discovery.
Just as our location in the solar system is optimized for habitability, so is our location in the galaxy. We inhabit a spiral galaxy, which means it's highly flattened. It has a spherical bulge in the center and has spiral arms. And we live about halfway between the center of the galaxy and the edge.
Working closely with astrobiologists Peter Ward and Donald Brownlee, Gonzalez compared our position in the Milky Way to other regions within an often hostile galaxy.
The galaxy has a lot of dangers, and perhaps the most dangerous place in the galaxy is the galactic center.
Well, in the center of the galaxy, this density of stars is very high, and there are more supernovas and stuff. And there are things that could harass life right in the dead center regions of our galaxy.
You also have the giant black hole at the very center of the galaxy. And if it were to have a close encounter with a star passing near it, it would rip it to shreds and form an accretion disk around it and emit lots of radiation, particle radiation and electromagnetic radiation, gamma rays, X-rays.
While a black hole, exploding stars and deadly radiation would make complex life virtually impossible near the galactic core, the outer edge of the Milky Way poses other challenges to habitability.
In the outer regions, the situation is much more subtle. We live on a planet made out of iron, magnesium, and silicon, and oxygen. If we went in the more distant regions of our galaxy, out towards the outer edge, the abundances of these elements are lower.
There probably aren't enough heavy elements to build Earth-sized planets that can support life. So there's a happy median between the dangerous galactic center and the outer edge of the galaxy.
Gonzalez, Brownlee, and Ward labeled this region, where complex life is possible within the Milky Way, the galactic habitable zone. Their theory was first published in 2001 and has since received growing acceptance among astrobiologists.
There's a lot more research that needs to be done to determine just how wide the habitable zone is, but I think there's general agreement that yes, there are definitely places in the galaxy that you cannot have civilizations because they're very dangerous, and there are places where you just have a very low abundance of heavy elements.
While these obstacles to habitability are minimized far from the core and edge of the Milky Way, Gonzalez has also identified large areas within the galactic habitable zone itself, which are less hospitable to complex life.
Even within the habitable zone in the galaxy, it's broken by the spiral arms, which are dangerous places. That's where most of the supernovae go off in the galaxy. That's where the star formation is taking place.
We don't want to be too close to a spiral arm. We want to be outside the spiral arm at about the right region of the galaxy.
It appears this is precisely where the Earth is located, in the relatively safe and uncrowded region between the Sagittarius and Perseus arms of the Milky Way.
Location is everything, and so we occupy that special place in the galaxy where habitability is optimized, threats are minimized, and we have enough building blocks to build an Earth.
Okay, so moving right along, get to number 20. Supernova eruptions. You don't want to be too close to one of those things. It can ruin your whole day. It'll blow your planet apart. It irradiates everything. And so if you've ever looked at a telescope or you've looked at a book on astronomy, you see the one in the top right-hand corner, that's called the Crab Nebula. It's about 10 light years in diameter. And it actually is the remnants of an exploded star. So if you're anywhere within 10 light years of that star that exploded, it would be very difficult to sustain life. And also when these stars explode, sometimes they don't explode as a nebula. Nebula means cloud, so it doesn't form a cloud. It forms either a black hole or it forms what they call a quasar. Sometimes you may have heard of the word quasar, other than at Motorola where they make television sets called quasars. But the quasar is emitting tremendous amounts of energy as a beam, and if your planet is in the way of that beam, if we were hit with that, that would terminate life on Earth instantly. Okay, 21, we're getting close to the finish. There's a lot more of things down below. The central star has to be singular, and the probability of that is 0.5, 50%. So this is a little cartoon, and you see two stars. One's kind of a red star, and the other one's kind of a blinking star. And those two stars are circling around each other. And if you have planets or other material that's attached to one of those two stars, you see that flying off at all different angles. The gravitational pull, when it gets too close, it can actually throw planets out of orbit into deep space. And did you know, how many people knew that half of the stars, the research says that half of the stars are two star systems, not just one. Half of the stars in the universe, half of them, 50% have two stars instead of one in the solar system. Did you know that, 50%? They never tell you that. So automatically, 50% of the possibilities for life are excluded. They never tell you that. And we get down to the last one, tectonic activity. That means the plates of the Earth, and I'll play the movie, but basically the tectonic movement means that the crust of the Earth, the very thin crust of the Earth, is moving underneath. They call it subduction, as it's passing under the continents, and that's carrying all of the debris. It's the garbage disposal for the ocean. It takes all of the waste material that's at the bottom of the ocean, and it slowly pulls it down into the center of the Earth to be melted again, and then you'll get it coming back out in the effluent of a volcano. So the Earth has its own cleaning system, which are the tectonic plates. And let me just play that for you.
If a recipe for a planet capable of supporting complex life really did exist, then what ingredients, beyond liquid water, might be required? The list of necessary factors continues to grow.
We live on this paper-thin crust. If the Earth's crust were significantly thicker, then plate tectonic recycling could not take place.
The Earth's crust varies in thickness from about 4 to 30 miles. It consists of more than a dozen tectonic plates that are in constant motion. This dynamic geology regulates the planet's interior temperature, recycles carbon, mixes chemical elements essential to living organisms, and shapes the continents.
So you can ask them, does the exoplanet have tectonic plate movement? So I'm at the end here, the last 3 of the 68 factors. If you look at the equation, we know S times T, that's 10 to the 26 times 10, so that's 10 to the 27. When you multiply all of those 68 probabilities, I've just described 22 of the 68 to you, but when you go through all of the 68 requirements, you come up with a number of 10 to the minus 99. So when you multiply 10 to the minus 99 times 10 to the plus 27, you get a probability of 10 to the minus 72. So it says there's one chance of 0.00072 zeros, 1, of having another planet in the universe that would be able to sustain life as our magnificent Earth that God has made for us especially. So it's, again, you know, the incredulity of trying to say that these planets have in the habitable zone, or they're close to their star, or this or that. There's so many factors. The other 65 factors just blow the idea out of the water. But nobody talks about that. They don't want you to know. They don't want you to think about that. And so I've been tricking you. There aren't 68 factors. They've gone through more carefully. The guy on the video said there were 20 factors. I use the data for the 68 factors. There's actually 200 factors, 200 critical factors. So the probability isn't 10 to the minus 72, it's 10 to the minus 250th that there's another planet out there that is exactly like our Earth, depending on the probabilities. So forget it. The answer is forget it. So let me conclude. I'm out of time, and I've just reached near the end of the presentation. Evolutionary cosmologists, the people in the newspaper and come on the television and say big words and spout great thoughts, and they all congratulate each other on how wise and intelligent and wonderful they are. They're trying to make you believe that the Earth is insignificant in the cosmos. But if you go down to the bottom, from God's point of view, Earth is absolutely significant. And it's the critical focus of God's creative, sustaining, and redemptive activities. And we have to remember that it was on Earth that the Creator himself became flesh. He bled, he died for our sins, and because of his redeeming action, created redemption for his people, for the people who call his name and say that he's Lord. He didn't do it, he's not doing it out in the stars. So extraterrestrials who are unrelated to Adam don't share in the original sin, and they're not restored because they weren't affected by original sin. Adam is a man. We have to remember that. And we had a God and man come to earth, live a perfect life, and die for our sins, and be raised on the third day. Hallelujah. I'm so thankful in my own personal life, and I think for everybody in this room. So that's kind of a review. I just wanted to end it with, when we consider the heavens, the work of your fingers, the moon and the stars which you have ordained, what is man that you're mindful of him? From King David. So I thank you very much for your attention.